Hi guys, I happen to be on campus today, so I thought while I was in the lab I'd shoot off a quick couple of videos going through the examples in the textbook from chapter 23. This is 23-8 and 23-9 about electric potentials. I strongly recommend that you go over these examples yourself and try to solve these problems with the textbook closed. Try to get the answer, open it up, go through the example. If you make some mistakes, try it again. These are pretty simple examples, but they are a good test if you kind of understood the process of converting, say, a differential element of area to a charge to dq or a dl to a dq. So they're good practice. The first example is a ring, a hollow ring of radius r, total charge q, and we want to know the potential at some distance x from the center of that ring. The thing to recognize about this problem, first off, is because the ring is thin, you're not differentiating along, or you're not integrating along any radius this way. And the distance from our point on the axis of the ring is always the same distance away from the ring. So r here is equal to the square root of x squared plus the radius of the ring squared. I'm using slightly different variables in your book, but that should be okay. So if we do this integral, everything under the integral is going to be constant. The expression for the potential at some point in space due to a point charge q is equal to 1 over 4 pi epsilon 0 q over r, not r squared. Potential goes linear. And if we want to add up all the contributions due to all the elements of charge dq, then that dv is just going to be equal to 1 over 4 pi epsilon naught dq over r. So the total potential is equal to the integral of that dv over the ring. 1 over 4 pi epsilon naught is a constant. That always comes out of our integral. dq over r, where r is the distance from our point in space to our little bit of charge dq, which in our case is always the same. It's the square root of x squared plus r squared. Notice x is a constant, r is a constant. That can all come out in front of the integral, and then we've just got the integral of dq, and the integral of dq is just q, the total charge. So this reduces to 1 over 4 pi epsilon 0, 1 over x squared plus r squared square root times q, total charge, the integral of dq around that ring. We don't have to do any geometry, we don't have to do any integral because we don't have any variables. So the integral of dq is just q, the total charge of the ring. And that checks out with the answer in your book. And just like we've been doing for all these problems, it's useful to think about the limiting behavior of this expression in some interesting case. What would we be interested in? What would reduce to something that we know and understand if we make x much, much bigger than r? In other words, if we're very, very far of that ring should look infinitesimally small, and it should give us the same result as a point charge, which hopefully you can see if I said you can look at it as taking the limit as r equals 0, or as x gets much, much bigger than r, this thing will reduce to q over the square root of x squared, or q over x, or just the potential of a point charge. Okay? Very straightforward. And you notice what we did not have to do at the beginning of this problem, because potential is a scalar, is we did not have to worry about that business where, oh, this part of the ring cancels out that part of the ring because the vectors point in opposite directions. Potentials don't ever cancel out. They always just add up. So we don't have to worry about the vector components, which makes calculating potentials in some sense easier than calculating fields. That's one of the reasons that the idea of a potential is a useful idea. The next thing your book does is it takes that result, just like we did for electric fields, and it uses it to determine the electric field of a disk that is not a solid ring, but a disk of charge evenly distributed over some radius. I'll call that radius capital R, we're on the axis of this disk, some distance x. Let's call the total charge of the disk Q. If the total charge of the disk is Q, then the charge density of that disk is the charge per unit area, because we've got a two-dimensional shape. We talk about its density in terms of its charge per unit area, which is Q divided by pi r squared, the area of the disk. If we're interested at the potential at some point P, we could integrate over this two-dimensional shape and find it that way. But your book takes the approach of considering the disk to be constructed of rings. Since we already just found the electric potential due to a ring, and we're going to make that radius of that ring r, because that radius is no longer going to be constant. We're going to be integrating that radius from the center out to the edge. Instead of just starting from the expression for a point particle, d is equal to the integral of 1 over 4 pi epsilon naught dq over r, we could do that, and we actually, I think, did it both ways for the electric field. But it's much easier just to say that the potential is equal to the integral of dv, where the contributors to the potential are just these infinitesimal rings, and we just found the expression for the potential of an infinitesimal ring. It's 1 over 4 pi epsilon naught q, and we're going to change that to dq. In other words, each ring will contribute an amount of charge to the potential equal to dq over square root of x squared plus r squared. And now r is not a constant. Okay? R is the radius of this loop, which increases as we integrate out from the center to the edge. And so this integral is going to go from r equals 0 to r equals capital R. The trick to these problems is how to express dq. How do we express this little bit of charge? What is the charge of this ring, this imaginary ring, in terms of the real disk? Well, what are we integrating over? We're going to be integrating dr, right, from the center of the loop out to the edge. What is the area of a loop with a tiny differential element of thickness? The surface area of that thing, which we can call dA, is going to be equal to the circumference, 2 pi r, times dr. Right? The surface area of this little ring is going to be the circumference of that ring, 2 pi r, times a little change in r. So dq, which is going to be equal to sigma dA, is just going to be equal to sigma times 2 pi r dr, or if we prefer, since sigma is q over pi r squared, that's q over pi r squared times 2 pi r dr, or does pi's cancel, just 2q over r squared times r dr. Okay? How does your book, well, we'll see how your book expresses the answer. We can either choose to express the final answer in terms of q, the charge of the whole disk, or sigma, the charge density of the disk. I prefer to do it in terms of q. So we'll substitute here for dq 2q over r squared times r dr. The only one of those things that is a variable is little r. Capital R is a constant. Q is a constant. So we pull those out front. We will have 1 over 2 pi epsilon 0. We've still got a big Q. I'll just separate these out. Q over r squared. And then we've got the integral from 0 to big R, okay, from the center of the circle out to the edge of the circle, of r dr over, or if we prefer, put this dr out here, r over the square root of x squared plus r squared dr. Okay? That's not a complicated integral to do. You guys know I hate doing integrals, but even I can look at that and say that r times x squared plus r squared to the 1/2, that integral is just going to be, sorry, minus 1/2, x squared plus r squared to the 1/2 times 2, right? And if I take the derivative of this, I get 1/2, that cancels the 2, this to the minus 1/2, and then I get 2r. Wait, do I need another 2? Maybe I need another 2. Or maybe I don't need that 2 at all. My answer here will be correct modulo a factor of 2. Let's look at this a little more closely. If I take the derivative of this, I get 1/2, that goes away, 1/2 times 2 times x squared plus r squared to the minus 1/2 times 2r. So I need another 1/2 out front, I think. I think you need a 1/4. Maybe I got that wrong. I'll check the answer in the book. But modulo a factor of 1/2, this is just x squared plus r squared to the 1/2. Evaluated from 0 to r. And there's a 1/2 or a 1/4 out there. We can check the book later and see what the book says the answer is. 1 over 2 pi epsilon 0. Q over r, 1/2, I think it's actually 1/4. X squared plus r squared to the 1/2 power. There's not much we can do with this. We put r in for r here at the top. Okay. We put r equals 0 here at the bottom. The answer we get, and I'll check this with the answer in your book, should be 1 over 2 pi, or q over 2 pi epsilon naught. X times 1 plus 1/2 r0 over x squared minus x. It's not pretty, but that's the answer that your book gets. We can test that by taking the limit of this again, as x is much, much bigger than big R. If we're far, far away from the disk, it should also reduce to a point charge, and I think we'll see that this is the case. We divide that whole thing through by 1 over r. The only term that will survive is this term, is x times 1 over x squared. So you get your 1 over 4 pi epsilon naught. Okay, this term goes away and this term goes away. So check my work here in the book. There's a factor of 2 here that's wonky because I didn't look up the integral before I started. But if you do that integral carefully, you should get the answer in the book. Practice those two until you can get them yourself without looking at the book. Well, at least until here. And then go on to the homework problems. The homework problems that I'll post after Tuesday's group of videos will be simple problems, basically redoing the electric field problems we did, looking at the potentials of different shapes. And so, like I said, the only real difference is that you don't have to bother yourself with the vector components, which actually makes these potential problems actually easier to do than the electric field problems. You might ask yourself, since potential is a scalar and easier to work with than the field, why didn't we just start with electrical potentials, then derive the expression for the electric field, and then go on and talk about integrating to find the force? And really the only answer is that historically that's not how the ideas came about. The first thing we discovered and measured was the force, and that's Coulomb's law. The next thing we did was start to talk about that force in terms of fields. And then later on, sort of in the middle of the 1800s, we started talking about fields in terms of potentials, scalar potentials in space. So the approach of doing fields first and potential second is a historical approach, even though conceptually the fields are sort of easier to deal with than potentials. As long as I'm here and talking at the video screen, it might be worthwhile to talk a little bit more about electric conductors and the relationship between conductors and fields and potentials. one of the things I mentioned in one of the little supplemental bits to one of the lectures is that conductors, if you've got a conductor at equilibrium, all the charge has to be on the surface. Okay. If it wasn't, if there was charges in the interior, they would repel each other and push each other to the surface. So when we're dealing with electrostatics, we can always assume that an electrical conductor, all the charges on that conductor are on the surface. What that means is at equilibrium, there can't be any component of the electric field parallel along the surface, because that component of the electric field would move those electric charges around. So a corollary to the fact that electric charges are free to move and at equilibrium we know they're not moving is that the electric field at the surface of a conductor is always perpendicular to the surface. Okay? This is only true of conductors. It's not true of non-conductors, insulators. But if this wasn't true, if the electric field had some component parallel to the surface, then the charges on the surface would move in that direction, and they would move until that was no longer the case, until there was no longer a tangential component to that field. So the electric field at the surface is always perpendicular. The other thing that this means is that since there can't be any force on any of those charges on the surface of a conductor at equilibrium, because if there was a force it wouldn't be at equilibrium, that means the potential difference between any 2 points on the surface of a conductor is zero. The difference in potential or potential energy per unit charge between any 2 points on the surface of a conductor is zero. If it wasn't, again, they would be moving around. And electrostatics, which is what we're studying in these 2 or 3 chapters, assumes that they're not moving around. That means that the surface of a conductor is what we call an equipotential. Usually when we talk about equipotential surfaces, we're talking about imaginary surfaces in space where every place on that surface the potential is the same. But when we're talking about the surface of a conductor, it is a literal physical equipotential surface. Every point on that surface has to be at the same potential. And it turns out that that's related to this fact that the electric field is perpendicular to the surface. Because, remember, the relationship between a field and a potential is that the field is equal to, we usually write it as the negative gradient, or if we prefer the triangle notation, negative gradient of the potential. And if you don't know what a gradient is in three-dimensional vector calculus, a gradient is a measure of the sort of rate of change in space in a particular direction of a field. And I'm going to record a whole video about this. I'll probably record it, it'll be Tuesday afternoon, and I'll post it on Tuesday or Wednesday, but that'll be the video that you're queued up to watch on Thursday. So this means that because the electric field is the gradient of the potential, that the electric field vector is always perpendicular to an equipotential surface. So the electric field vector on the surface of a conductor is always perpendicular to the surface of the conductor because the conductor is an equipotential surface. I will go over this fact, and I'll talk a little bit about the gradient for those of you who haven't taken Calculus 3, just in a sort of intuitive way. Because understanding the relationship between potentials and fields, and being able to, if I give you a picture of an electric field, to draw the shape of the equipotential surfaces, or if I give you a picture of a bunch of equipotential surfaces for a field, to draw those electric field vectors. Being able to do that gives you a really intuitive feel for the electric field and electric potentials in space, and I think that's really, really important. So I'll record a couple of videos about that this week. So on Tuesday I'll post a couple of problems, integrating defined potentials, go through these examples a couple times until they feel pretty automatic to you, and then we'll talk about equipotentials in the next set of videos, and that's what your lab activity is going to be. I'll probably post it, well, I'll post it as soon as I post the videos about the gradient and equipotentials. the lab activity is playing with that same electric charge simulator that we played with last week, but actually mapping the equipotential surfaces in space and predicting the shape of those equipotentials and what they look like. Okay, so I'll go ahead and end that there, and I'll post these videos for Tuesday and a couple more for Thursday, and then we'll be, I think, done with electric fields in space and ready to go on and talk about things like electrical circuits.